Capacitor. First of all, we will see the definition of capacitor. Capacitor is a passive two-terminal electrical component that stores electrical energy in an electrical field. So first of all, capacitor is a two-terminal element. Here we can see this is the symbol for capacitor. It have two terminals and it is a passive component. Then it stores electrical energy in the form of electrical field. So this is the definition of capacitor. Then next is capacitors oppose any change in voltage. So if there is a voltage change, then it opposes the sudden change in voltage. Capacitors store energy, not charge. So remember that capacitor stores the energy and not the charge. All capacitors consist of two thin parallel plate metal sheets or foils called plates very close to each other. So here we can see capacitor consists of two plates parallel, and here there is a space in between them. These two plates are separated by insulating material, which we call dielectric. Now here we can see there is a separation in between them, and this space is called dielectric. Dielectric material may be air, mica, oil, impregnated paper, etc. So here this space may be air or mica or any other dielectric material. Mostly capacitors are named according to their dielectric, like mica capacitor, paper capacitor, etc. So suppose if this space contains mica, then it may be a mica capacitor, or likewise. Now here we can see this capacitor is connected to a external source of DC potential difference. So it is connected to a battery or a voltage source. Now here this positive terminal is connected to this plate. So this metal plate becomes positive. Here the charges are all positive. And this negative terminal is connected to this plate. So all charges on this plate are negative. And this space is the dielectric. Dielectric with permittivity, which is represented by epsilon. Now these are two metal plates, and this is the space in between them, and this is the electric field. So this is the electric field, and this plate contains positive potential and this plate contains negative potential. The distance between these two plates is represented by small d. It is the distance and it is in meters. And the area of plate is represented by capital A, and it is measured in meter square. This is the symbol for capacitor. These are the two plates, these are the two terminals, and this is the space in between them, which is dielectric. Again, any two conducting surfaces separated by an insulating medium exhibit the property of a capacitor. The conducting surfaces are called electrodes, and the insulating medium is called dielectric, as we have already seen again. So here these are the two plates and this is the dielectric. So these two are called electrodes and the insulating medium is called dielectric. A capacitor stores energy in the form of an electric field. So this capacitor stores the energy in the form of electric field that is established by the opposite charges on the two electrodes. The electric field is represented by lines of force between the positive and negative charges and is concentrated within the dielectric. So this is a typical capacitor. These two are the metal plates, each with area A, and the area is measured in meter square, and the space in between them is insulating material, which we call dielectric, with permittivity epsilon. And this is the distance in between these two plates, which is measured in meters. So here this capacitor connected to a voltage source again, and this is the symbol for circuit symbol of capacitor. When a voltage source V is connected to the capacitor, as in figure, the source deposits a positive charge Q on one plate and a negative charge minus Q on the other plate. So here we can see this positive Q is for this positive terminal of this battery or voltage source, and here it will deposit the negative charges on the other side because it is connected to negative terminal of the battery, so which is represented by minus Q. Q represents the charge. Remember that the capacitor is said to store the electric charge. The amount of charge stored, represented by Q, is directly proportional to the applied voltage V, so that Q is equal to C into V. So here this charge is directly proportional to voltage, and this C is the proportionality constant. This Q represents charge, and this C represents capacitance, and this V represents voltage. So remember that this is the formula: charge is equal to C into V, where C, the constant of proportionality, is known as the capacitance of the capacitor. The unit of capacitance is farad, which is represented by symbol capital F. So this capacitance is measured in farad, voltage is measured in volts, and charge is measured in coulomb. Although the capacitance C of a capacitor is the ratio of the charge Q per plate to the applied voltage. So here the capacitance, we can rewrite this as C is equal to Q upon V, charge upon voltage. It is the ratio, capacitance is the ratio of charge upon voltage. It depends on the physical dimension of the capacitor. So here remember that capacitor is the ratio of charge upon voltage, but it does not depend on charge or voltage. It depends on the physical dimension of the capacitor. For example, for the parallel plate capacitor shown in figure, the capacitance is given by, so here this is the formula for capacitance: C is equal to epsilon A upon D, where C is the capacitance, epsilon is the permittivity of dielectric material, and A is the surface area of plate, and D is the distance between plates. So remember that this is the formula for capacitance, where A is the area, surface area of each plate, D is the distance between the plates, and E is the permittivity of the dielectric material between the plates. The current flowing through the capacitor is given by, now here this is the formula for current through capacitor: I is equal to dq by dt, where this q represents charge and this d by dt represents change with respect to time. So change in charge with respect to time. So again we can rewrite this as I is equal to C dV by dt. We can replace this charge by C into V. and here the C is constant, so it will be C dV by dt. The current in a capacitor is 0 if the voltage across it is constant. That means the capacitor acts as an open circuit to DC. So remember that capacitor acts as an open circuit to DC. A small change in voltage across a capacitance within 0 time gives an infinite current through the capacitor, which is physically impossible. In a fixed capacitance, the voltage cannot change abruptly. That is, a capacitor will oppose the sudden change in voltage. So it will oppose the sudden change in voltage. Remember that capacitor opposes the sudden change in voltage, and capacitor acts as an open circuit to DC. The capacitor can store a finite amount of energy even if the current through it is 0. So remember that capacitor can store only a finite amount of energy. A pure capacitor never dissipates energy but only stores it. That is why it is called non-dissipative passive element. However, physical capacitors dissipate power due to internal resistance. So this is about capacitors.